So good afternoon, everybody. It's a great honor to be here. I would like to thank the organizers for asking me to give this last lecture of this most interesting workshop. I was delighted to accept, and especially to be included among such a set of distinguished speakers. Now, you might say, well, wait a minute, aren't you one of the organizers yourself? And of course, the answer is yes. But I was not involved in the decision to include myself in the program. So I want to thank the other organizers for giving me this opportunity. So like many of the previous presentations, I would also like to start with a story. But that story would lead me to the technical part of this talk. So please bear with me. So let's go back to the American Control Conference in 1991, which was held in Boston, in fact, like this year. And I was chairing the 4 to 6 p.m. session on Friday, which was the last day of the conference, because I had a paper in it. So it was about 6:15 p.m. I was leaving the conference room, really tired after a 3-day conference and just wanting to go to my hotel room, when this gentleman approaches to me and he says, "Oh, excuse me, my name is Qasim Sinamohidin, and I work at Johnson Controls Research in Milwaukee, and I'm doing work related to fault diagnosis in heating, ventilation, and air conditioning systems. And I really believe we need to look at this problem using a discrete event systems approach." And I said, whoa, okay, whoa, wait a minute. Can you start again? So parsing the name, his name was Qasim Sinamohidin. Okay. So he gave me his card so I could read his name. And to make a long story short, he was a researcher at Johnson Controls who actually did very useful work for his company in the 70s during the energy crisis. So he was convinced that he was playing with some models to diagnose HVAC systems, and he was convinced the right way to approach that was from a discrete event systems perspective, or an event-based perspective, as a complement, of course, to all the well-developed continuous state space approaches. He came to Michigan about a year later in September 1992. Now, at the same time, we had two very junior but very talented Ph.D. students, Meera, Sampath, and Rajas and Gupta. So then I was thinking, okay, I know a little bit about discrete event systems. That's my area of research. I know nothing about diagnosis or HVAC systems. So I went to my colleague next door, Demos. I explained to him the problem. I said, "Are you interested in working with us on that?" And he said, "Yes." So we got Demos interested. And this was the beginning of a beautiful research collaboration. We already had the friendship. Okay? And so what happened in those few years from 92 to 95 is we worked on developing an approach to diagnose faults, but essentially unobservable events. They don't have to be faults. In an event-based approach using logical models, so no time or no stochastics. And it was a language-based approach, much like the theory of supervisory control that had been initiated by Ramage and Wallam several years before, using finite state automata as a computational tool. So we came up with a formal definition of diagnosability, a notion of a diagnoser automaton, and we had this collaboration, of course, with Johnson Controls. Meera, Sampath went there on a summer internship, and it led to the dissertation of Meera Sampath. We jointly supervised her. And 2 papers, one in the transactions on automatic control, which had all the theory. And then there were these relatively new transactions then called control systems technology. So we called that our public relations paper, quote unquote. What it had actually was more of the modeling procedure and a lot of HVAC examples in there. And we developed a software tool to implement these constructions. Now, Demos doesn't like to brag, but I thought I wanted to mention that because maybe many people in the audience are not aware. But this work has been extremely influential in the field. First, in addition to Meera, Sampath, we co-supervised 2 more students after that Rami Debouc, who unfortunately could not be here. He works at GM, but he had actually he would have needed a self-driving car because he has a foot injury, right foot, so he can't drive. And subsequent to that, Olivier Contant, who is here in the back of the room. Want to say hi? Okay. And then Demos supervised David Thorsley, who worked also on this problem, and I supervised several other students. But most importantly, literally, I'm not exaggerating here, but hundreds of researchers have written papers that have extended the theory that was initiated then. And it's a comprehensive theory that applies not only to automata models, but also Petri nets. And there's a wide variety of diagnosing architectures that have been studied. It goes from the polynomially decidable to the undecidable, from diagnosis to prognosis or fault prediction. There's even recent work where people are using SAT solvers for testing diagnosability of systems in particular, as well as distributed cases. There have been several applications. There's a recent survey paper that is referred to here. Actually, it's primarily the work of Janan Zaitoun based on a plenary lecture that he gave. And all my references are at the end of my presentation, so when it's posted, you'll be able to see them. So we're really not far from 101 definitions, hence the title. But of course, I'm not going to go over all of these definitions. So I thought it was worthwhile mentioning that as a way of introducing this talk. So now I'd like to maybe have a little bit of a brief review of that definition of diagnosability. Perhaps people in the audience are not familiar with that. And that will take me to the lack thereof part of the talk. So the viewpoint here is we have a dynamic system. It has some outputs through sensors. So it's an event-based framework. Not all events are observable. So E sub O here is a set of observable events. And then we want to build a diagnostic engine that will do model-based inferencing about the occurrence of certain distinguished events called fault events here, but as I mentioned, they need not be false. Okay. So in terms of saying, yes, I know for sure that such an event has occurred, no, I know for sure that it has not occurred, or I do not know. Okay. So, and I also want to mention that we were influenced, of course, there was, we read a lot of papers in those days, but we're also influenced by Feng Lin, who had just spent a summer at Ford. Feng Lin is at Wayne State University here in downtown Detroit. He had just spent a summer at Ford working on diagnosing mixed signal circuits and exhaust gas recirculation systems. He had come up with a notion of diagnosability as well, and then that inspired ours. So so for simplicity, let's just say we're dealing with a finite state automaton denoted by G. So the notion in words, and I'll show you in mathematics in a second, is the unobservable event of interest, say the fault event, is diagnosable in the language generated by the system, that is a set of all possible strings of events, if every occurrence can be detected with certainty in a bounded number of events following its occurrence. Okay? So every single occurrence has to be detected in that manner. So this is the definition as it was stated in the original 1995 automatic control paper. Let me simplify it a little bit because we also had added the notion of a fault partition, but it's not essential for the discussion. So I promise it's simpler than what Venkat was presenting this morning. So we just have 3 quantifiers here, okay? So the point is, let's see if this, actually, Dimitri had the best pointer of the whole group of people here. It's not that great. So there must exist an integer such that take any string in the system, any sequence of events at the output, if it contains a fault event, take any continuation of that string, that's what this notation means. If that continuation is longer than n, then the diagnosability condition must hold. That is, you must be able to say yes with certainty here in your reasoning. Now, how does your reasoning work? What has occurred so far is a string of events ST. Of course, you don't see all of these events, so you have to project the unobservable events out. So that's what this projection is. So excuse me, ST is what occurs, P of ST is what you see. So your reasoning is going to be do the inverse projection, intersect with the system model, essentially find in the system all the strings of events that are consistent with what you have seen that could have led to these observations. If all of these contain the fault event, then you know for sure that the fault has occurred. So your model-based inferencing says everything I'm seeing everything that is consistent, what I'm seeing must contain a fault event. So in the language world, this is what you do. Then you have to do that construction in an automaton world, and I will tell you that in a second, okay? So how do we do that model-based inferencing? We don't do it in that way because these languages, these automata can have cycles, so these languages can have infinite cardinality. So using an automaton, what you can do is you need to remember at each state if you reach that state by executing the event, the fault event that you're trying to diagnose or not. So what we do is we do a parallel composition operation with a label automaton that has two states, no or F faulty, that is reached after F. So that does the state splitting. Now it's still non-deterministic here in the sense you have an observable event. So what you need to do is you need to do the determinization of that automaton, which is a very standard operation in automata theory. We call it building the observer of that label automaton. And essentially this implements this inferencing here, producing a state estimate, which is the set of all possible states that the system can be in at that particular time. Okay? And the resulting object, that's what we call the diagnoser. Now, a few years later, people realize, okay, so you might worry here because you have to do the subset construction. It's exponential. It's almost unavoidable in partial observation problems that you'll have to do something like that. I like to quote Moshe Vardi, who says that exponential is the new polynomial. At least it's better than doubly exponential, right? Now, people realize that if you just want to verify diagnosability, you can do that in a polynomial way. The reason is, in my definition here, I had a for all and a for all. The negation of that is there exists, right? I told you the math was easy. So now this means you just need to build two strings that will lead to a counterexample. And you can do that by doing a composition of two copies of the system, where in one copy you remove the fault events, in the other one you leave them, and then you have a there exists n here. So if you want to violate, that means for all n, you'll never be able to know for sure. So that means you must get into a cycle where the two strings have the same projection. And if they have the same projection, then you cannot distinguish them, right? So the condition in the world of this structure here, which we call the verifier, the Europeans call it the twin plan, because you compose two copies of the plan. So it's a cycle condition. It's similar here in the diagnoser, which I guess I didn't say that. I just stopped that. You build the estimate, then you have to check a similar cycle condition in the diagnoser. Okay? So that's the state-based testing of the property of diagnosability. Now, if you want to implement your diagnosis online, of course, you have to build a diagnoser. This guy doesn't do the diagnosis for you. Okay? So, and of course, as I mentioned, this is just the most basic set of results, and they're 20 years old, so maybe they'll be reinvented soon, as I've been joking in the past 2 days. We'll see. But at least I think people still read these papers, right? If you look at Google Scholar, they still get cited. So now I'd like to move to the lack thereof part of the talk and discuss a property that is called opacity. It's close to the negation of diagnosability, but not exactly that. It originated, to the best of my knowledge, in the computer security literature by Laurent Mazaret. He was analyzing cryptographic protocols, and he formulated that information flow property that is very simple, but because it's simple, it's also very general, and it can be used in suitable context to capture notions of anonymity, secrecy, or privacy. And I will focus on the privacy aspects in this talk. So the good thing about opacity, it's easy to describe. So it involves a secret. So because we're talking about finite state automata models here, let's assume that a subset of states of the system is the set of secret states. So it's X sub S. Okay? And there are many variations, excuse me. So the simplest one that's sufficient for the purpose of our talk today is current state opacity, CSO. So there's other notions. So here you're trying to hide something about your current state, but it could be that you're trying to hide something about the initial state where you started from. It could be that you want even to do more to keep something private at the current state, but also no one should be able to figure out in the previous case state. So that's case step opacity. It's a form of smoothing. Okay. So the context here is there is a system that has a secret. It has its output behavior. I put a little projection P here to emphasize not all transitions, not all events are observable. And then there's the observations coming to the outside world, and there's a potentially malicious observer here. Now, there may be legitimate recipients down, but someone is looking, and this person knows this model, and it knows P. Okay? So it's trying to determine if the secret is being revealed or not. But remember, this has unobservable events, right? So if this guy cannot do better than basically build the observer that I mentioned earlier, or doing the state determinization or the subset construction, if you wish, as they like to say in automata theory. So it will never know for sure the state of the system, but perhaps your state estimate revealed a secret. Okay, that's what you would need to check, depending on the form of your set of secret states XS. So in words again, and I have the math on the next slide. So the secret should never be revealed with certainty to the external observer, potentially malicious. So we call him the intruder, but actually that's a passive observer. There's no attack model here. Okay? Bayes that has access to the system model and online observation. So as I said, that's where it the connection to diagnosability. It's kind of like saying the secret is not diagnosable, but it's actually stronger than that. The point is that deniability of the secret should always hold based on facts. Okay? So why did I underline facts here? What's the most popular form of deniability in today's society? Lying. Well, you're not allowed to lie here, okay? It has to be based on facts. So if there is a system behavior, a string of observations that reveals the secret, there has to be another one. So say that ends at the secret state in this case. There has to be another one that does not reveal the secret, and that is equivalent from the point of view of this observable behavior. So it doesn't say how many, it just says one. So at least based on what you see when I use my cell phone in this building, I could be here, I could be in the coffee shop, but you don't know for sure, right? And I'm not putting probabilities here, although you could. Okay? So examples of opacity that we've used in some of our work, for example, if someone has a mobility model and you issue queries from your phone, maybe you want to hide that you are in some building on campus at a particular, when you're moving around. So so here the system model, the automaton is your mobility model, okay? In the context of Internet of Things, when the sensors are deployed, perhaps you have sensors all over the building, and the secret is you should never reveal that the CEO is alone in her office, for example, okay? So, and there's lots of other examples. Again, it's all a matter of what you want to formulate in terms of what is the secret and what you wish to capture. Of course, it is model-based here, so there has to be like a mobility model or knowing where all the sensors are located on the various rooms on the floor of a building and so forth. So mathematically speaking, so I have again this model, again represented in the form of an automaton, because we want a language-based formulation. Okay. We have a set of secret states. So now it says for any initial state, for any strings that start from that initial state, if that string takes you to a secret state, so this is a string that reveals the secret, there must exist another initial state and a string that starts from that initial state such that that strings end in the complement of the set of secret states. And it has the same projection. Okay? So that's the plausible deniability. And so I have for all and there exists. Okay? So that's why it's stronger than diagnosability, because if I negate it, there exists and for all. And before I add there exists and there exists. Okay? So one of consequence of this one, you cannot get away in testing it in polynomial time in terms of number of states of the automaton. You have to absolutely do the subset construction to test it. Okay? So it's been proved, that's been proved. So the twin plant approach or the verifier approach fails. Okay, so that's what the definition is. And again, it's general, but that's kind of the beauty of it. You can use it in different contexts. So what we're really interested in is what can we do if opacity does not hold, okay? So what people have tried, especially now that people in the discrete event systems community got interested in that property because it's related to diagnosability. So people said, well, let's do control. So I'm going to put a supervisory controller here that reads my sensors and has some actuators, so there's some controllable events here. And I'm going to try by control to remove the behaviors that reveal the secret. Okay? So I'm going to shrink the system behavior. So I want to make the control behavior, the standard notation, we call it S/G in supervisory control. It must be opaque, but then we don't want to restrict more than necessary, so you should be as permissive as possible. Now, in general, such solutions are not unique, but there are ways to solve this problem. Most recent method developed by my current student, Xiang Yin, who is here in the room. And, but this means you're allowed to go and tweak the system behavior, okay? So this is more at design stage, if you wish. So it could be the system is already deployed, but you want to enforce the secret. So then what can you do? So we're inspired by work by Schneider in the security literature. He had a notion of an edit automaton. So we thought, and this is with a former student of mine, Yichin Wu, who graduated a couple years ago. We thought, what about you leave the system intact, but we insert an interface at the output here that will add additional observable events, and that will produce modified behavior. And that modified behavior will be such that the intruder will not be able to detect the secret. Okay? So we insert events. Now these events must look the same what you insert from the point of view of the intruder. Okay, so the inserted events and the genuine ones are indistinguishable from the point of view of this guy. Now, it's possible that there's the legitimate recipient down the line has a way of distinguishing these packets. Maybe you can imagine there's a field in a packet where you put 0 and 1, the intruder doesn't know that that field has any meaning. Okay? So now what are the conditions under which such an insertion mechanism would work, or what you would want that to accomplish? So number one, this is an interface you're adding. This is like an additional app on your phone, for example. So it should be able to take as input everything that the system produces as output, because it's not interfering in the system. Now, this is not noise, right? So it's not just inserting random events. What it's inserting must be such that the net result must be something that is possible in the original system behavior, and it should not reveal the secret either. So the modified behavior must always be such that it's observationally equivalent to an existing non-secret behavior of the system. So you're matching to something that does not reveal the secret. So therefore, when you do that, you enforce opacity. Okay? So the issue now is you'd like to synthesize that module automatically, given the description of the system and what is the secret that you're trying to enforce. And you can do that. What we synthesize is essentially an input-output automaton, which is a finite encoding of that insertion function. Remember, the domain of that function is infinite in general in terms of sets of strings, but everything works. We're assuming it's finite state automaton, okay? So we're able to synthesize a finite state input-output automaton, like here, a very simple example. Along this transition here, if the system outputs a B, then the insertion function will insert an A before that B. Okay? So what the intruder will see is AB, and so on and so forth. Now here we just have a few states. Okay? So that's what we know how to synthesize. So how am I doing on time? Okay, I'm good. Okay, so more than that, we actually implemented, I should say Ichinwu, a toolbox that does the calculation of the synthesis of the insertion function. So I want to tell you a little more about that synthesis mechanism, because that's an interesting part from a technical viewpoint. So, well, first you'd like to determine if such an insertion function exists, because it need not, there are cases you may not be able to solve in that manner. So the way we do that is we build a discrete structure. We call it the all insertion structure. And it embeds all valid insertion functions in a game-like structure where you have the system playing against the insertion function. So it's a game against nature. Now you say, well, why did you cross out the word game? It's because each time I talk to Demos, he said, well, that's not a game. That's a worst case analysis. And I say, I agree with you, but everyone in automata, they all call that games against nature, games in automata. So, but anyway. So Demos, I did cross out the word game. Okay. So it's a worst case analysis. And so once you build that structure, I'll tell you a little bit about it, but I don't want to go into too many details. The synthesis problem, so if that structure exists, the synthesis problem is you just extract one insertion from that insertion function from there. So the way to do that is kind of interesting, I think. So there are 3 steps. So the first step is you take your estimator. Okay, this is like the state estimates that are built after determinizing the system model. And suppose here, for example, this 4 was the secret state. It's in red. And if B occurs, then this is 4 under the red X here. So that means the secret is revealed. So, but you cannot prevent the system from outputting that B. But here what I'm saying, I'm not allowed to go there, so I'm going to prune that out. Okay? Then I'm going to create another copy with everything. On top of that, I'm going to add self loops for everything that I can insert. Here there's only 2 events in the system, A and B. This one is unobservable, so I cannot insert unobservable events. I only insert observable events because I'm attached at the output of the system. Okay? And then I'm going to compose these 2 structures using a standard parallel composition of automata, which means you synchronize on common events. So this guy cannot go there, so this guy will be forced to self-loop to execute that one. So what it means is when you combine the 2 in some sense, you'll have a copy on the left that will be the fictitious state estimate as inferenced by the intruder, and this one will have the true system state because when you self-loop, you don't change the state. These are the inserted events. And then you can differentiate between the 2 sets of transitions, the genuine ones, which is a solid transition here, coupling with the solid transition here, and the fictitious inserted one, which is a solid line here, coupled with a dashed line here. So you just need to memorize the 2, okay? So you get, but this is polynomial growth. But of course, the initial step you had to build these structures, that's where the subset construction occurred. But from there on, it's polynomial, okay? So then the next step is to, how late did I start? 10 minutes late? Yeah? Okay. So you unfold that to get that game-like structure that I described before. Pardon the use of the word game. So the idea is to think of it as follows. So now remember my states are paired because I took the product of 2 things. That's why I have pairs here. Remember the left estimate is the fake one. The right one is the true system state. So I call this my information state for the system player. And then I have the possible outputs that the system may execute. And then I create these intermediate states for the information state for the insertion function player. So the way to think of it is, this is the state of my product structure that I built. B is the event the system is trying to output. This is, here I'm going to put all the possible insertion decisions that are possible according to the result of my product here. So that's why it's kind of an unfolding this product. but it doesn't unfold it more than, again, a growth in the number of states times the number of observable events. Okay? So system outputs an event, insertion function decides if it's going to insert anything before that, along with that event. So B by itself or B preceded by something. And then you keep going like that. Okay? Now this is finite, so this is good. And there's one more step, is potentially to prune. That's explained on the next slide, because you might get into a situation where you get to a state where the insertion function must play, but it has no move. There's no event defined there after the result of your unfolding. What it means is, essentially, I'm stuck. The system is outputting a B. I don't have a way to react. For that B, there's nothing I can insert. In other words, anything I would insert would reveal the secret. Okay? So it means the system should not output that B, but I cannot prevent the system from outputting that B. That means I should not go along that path. I should not have chosen that insertion here because it takes me to a deadlock. That means I should have chosen that insertion. Okay? So then you keep iterating. Now this requires iteration, but it's okay. So you delete the previous insertion, and then you prune like that. Now some of Demos's former students here took my discrete event systems class when they were in school, so this problem is actually the same as the standard supremal controllable sublanguage calculation that Ramage and Wanham did back in the late 80s for the criteria of non-blockingness. So you can think of it like that, if you remember what the supremal controllable sublanguage is. If you don't, that's okay. The only thing to remember here is I need to do that pruning on that structure. And then when I'm done pruning, the worst case, I might prune the initial state. I'm left with nothing. That means there is no insertion function that exists. But if I'm left with something, that is if this all insertion structure AIS is non-empty, then I know that a valid insertion function exists that will guarantee opacity. So what do you do once you have that insertion function? Well, you have a synthesis problem. So it's very easy if your structure is non-empty, because at every system state, you have to keep all the possible system outputs, because those are unpreventable. And at every state, the oval ones where the insertion function plays, you just pick one choice, because all of these choices are correct after you've done your pruning by construction. Okay? So now you can easily think, maybe I can go to an optimal synthesis problem, because now the result of that previous construction is I have my optimization space. I have all the valid solution. Now you can imagine there's a cost to insertion, because, for example, in my cell phone example, you have to insert additional packets or send more requests to the server when you insert events, so that's costly. So you can put a cost. And then you end up with one of two, at least, optimization problems. So first, remember, there may be loops in the system. So you have to look at what's the worst case total cost. If you don't insert in a loop, then you are okay. The worst case total cost might be finite. Then you just do basically a dynamic programming algorithm over that weighted automaton where you've put the costs on the transitions, okay, on the insertion transitions, not on the system one. If not, if you're obliged to insert in a cycle, then you can look at the worst case average cost criterion per system output. And it turns out there's nice algorithmic procedures here from Zwick and Patterson that allow you to solve this problem. It's computationally more than the dynamic programming one here, but at least you can still do it polynomially. So it's quartic. So. But I will skip all the details. They are in the papers. You know what I say in class when that happens? You're looking. I just say, if it's for me, tell them I'm busy. So. But you know, the joke is not so good after so many years. So, okay. So I'm almost done for the technical part here. We'll just be back on a little over on schedule, and I'm not going over my 45 minutes. I just want to tell you one more thing. So Praveen was talking about deep learning. Well, what about if the intruder learns the insertion function? It's not entirely clear to me how one would do that. I mean, probably you need to go to a stochastic framework, but let's say that maybe you disclose the insertion function, or the intruder learns it in some mechanism. Is it going to change anything? And then my first reaction, well, no, because the intruder cannot distinguish genuine events from inserted ones. So even if it knows the insertion function, it still cannot differentiate the string. But that's not true. And we do a very, very simple example. We can do that in discrete event systems sometimes. We're using just a few states. So this is your estimator. 8 and 7 are the states where the secret is revealed. So if B occurs, the secret is revealed. So I can insert an A before. So if B occurs, I map it to AB. AB does not reveal the secret. But then ABC reveals the secret. So what I do is I map ABC to DABC. Okay? So suppose the intruder observes AB. If it doesn't know the insertion function, it cannot do anything. Okay? It doesn't know if it's what happens because it is, it sees AB. But if it knows the insertion function, it's going to say, aha. If it was truly this AB, it would have been changed to DAB. Therefore, it was this B. Therefore, I know the secret is revealed. So the bottom line is not every insertion function that works when it's unknown to the intruder works when it's known by the intruder. Okay? So, however, we have a theorem which is almost proved, but I'm confident we still have a few steps to work out completely. This is with one of my current students, E.D. Jing, who's here in the room, but I'm confident enough that I'm putting it on this slide. So that that's lots of pressure, right? If there exists an insertion function that works when it's unknown, then there exists, it's an if and only, there exists an insertion function that works when it becomes known, okay? So that's what we call public and private. It works both private or public. So that would be that's kind of interesting. It means you can still solve problems when the insertion function becomes public. I wanted to say that opacity captures, in a very general framework, several relevant security and privacy requirements. And it's related to diagnosability. It's also related to a property called observability in discrete event systems, but I didn't talk about that. It turns out that you can map diagnosability to observability. So that's very interesting. So from my viewpoint, in these systems under partial observation, even though formal language-based models are very simple, they have very little structure, but they're rich enough to capture meaningful informational properties about the system. And that's one of the things I've learned from Demos, is that the information structure is the fundamental concept, not necessarily the class of mathematical models. Now, that's not to say that the class of mathematical models will influence the kind of verification or synthesis work you can do. And in the world of automata models, we don't have very much structure. So we face the state space explosion problem, right? Now, if you allow me, I'd like to make a few personal remarks. I am not 65 yet. I'm several years younger. But I think I've been here long enough to make a few comments, especially aiming at the young people in the audience. So, you remember my story at the beginning of the presentation about meeting Qasim and Muhyiddin? So don't believe your parents. Do talk to strangers at conferences. You never know where it might take you, okay? Now this I could not resist. I apologize. I know it's a cliche, but there's a reason why it became a cliche, right? So I think... Now, Demos, we had a very nice event last night. It's unfortunate that not all of the attendees of this workshop could come to the dinner, but all of Demos's former students made very moving testimonials to his skills as a researcher, advisor, human being. And I didn't make any comments then because I wanted to reserve these comments for now. And one of the things Demos said, very interesting, is that I promise I made that slide before I heard your speech, so I made those slides a few weeks ago. But you said always learn from your research collaborators and your students, so that's one of the things that I want to emphasize. And it's certainly something I learned from you, and more than that, it's actually, I've learned a tremendous amount from you over our collaboration over these many years. And when I was graduating at Berkeley, my advisor, Eugene Wong, gave me some advice. He said, set your own standards and follow them. And I think that's very good advice. And, but how do you set your own standards? I think you need role models, right? And so I think Demos, it was clear yesterday that you were an amazing role model for all of your students, and I can say the same for me. You were an incredible role model. I think I was so fortunate that when I arrived here at Michigan, your office was next door to mine. So, and among the many things that we admire about you, I want to mention a few things. So, and they were mentioned yesterday, but they're worth re-emphasizing today. Number one, I think, is your unwavering high-quality standards. Number two, your scholarship. And number three, your academic integrity. And those are, that's why you're a role model. So I certainly hope that we will continue to have a beautiful research collaboration for many years. As Aditya, where's Aditya, pointed out yesterday, this is not a retirement celebration. This is a celebration of accomplishments. It turns out the number 65 has a special meaning, so it was a good excuse to do this workshop. And not only I hope that, and I know that we will always remain friends. I have actually one more slide I was saving for the very end. This is a photo from 1994. So this is Meera Sampath, who could not attend the workshop, as you know. And I saw her not too long ago, and I can assure you she looks exactly the same. But it's obvious that the same cannot be said for some of the other people, including whoever said yesterday to me, you look the same. Well, this is, you may want to revisit your statement. And on the far left is Raja Sengupta, who's now a professor at Berkeley. And this is my colleague, our colleague, Jim Frudenberg. So let's see if I can say that right. Hornia Pola Demo. Thank you.
I'd like to welcome a really impressive group of speakers, as well as other attendees. I actually think I know most of you. If not personally, I certainly know you by name and by reputation.